Okay, so let's continue with our discussion about Zener diodes. As mentioned last, well, not mentioned, as covered last week or last class, Zener diodes are specifically formulated to operate in the reverse bias. And so as a brief recap, let's bring that up. Page 24. All right. Zener diodes are specifically created or fabricated and designed to operate in reverse bias. In the forward bias, they operate as normal regular diodes. In reverse bias, because of the heavy doping and the design and the geometric design of the junction, the diodes break down at a specified or specific voltage. Okay, so we are operating in the reverse bias. In the reverse bias, typically diodes do not break down until the reverse bias voltage reaches tens of volts. Okay, you can find diodes off the shelf commercially available that can handle up to hundreds of volts in reverse bias. Okay, so normal diodes, normal silicon diodes, germanium diodes do not break down at lower voltages, whereas Zener diodes are specifically created to break down at a specific voltage. And that breakdown voltage can be anywhere from like 2 volts, 3 volts, all the way up to tens of volts. Okay. So if we create a model in the forward branch, it behaves like a regular diode. So very similar to a regular diode. And in the reverse bias, it's off until the external applied voltage crosses its Zener voltage. Once it crosses the Zener voltage, which is the breakdown voltage, current will start flowing. So we can model it as a resistor in series with a voltage source because it is providing a constant voltage at the output. Now, semiconductor fundamentals aside, what we want to do is we want to look at the Zener diode as an off-the-shelf component that you can use, for your circuit applications. So in the Zener characteristics, you can see that it conducts in both directions. This is true of any diode, right? A diode, regular silicon diode, will conduct in forward bias. It'll conduct in reverse bias also, but that breakdown voltage in a regular diode is quite large. In a Zener diode, again, normal Zener diodes that we use for electronic applications, it's somewhere between 15 to 20 volts. Okay. Typical DC power supplies require 3.3 volts, 5 volts, 12 volts, 15 volts. And so most Zener diodes that we use for electronic components are somewhere in the range of 15 to 20 volts, starting from 2 or 3 volts, of course. All right. So this slope that you see after breakdown in the reverse bias is far steeper than what you see in the forward bias. Okay, and forward bias is fixed, right? Forward bias voltage drop is 0.6 to 0.7 volts. So that is fixed. We can't change that. Doesn't matter what kind of design we create, doesn't matter what kind of doping we create. Forward bias does not change. Reverse bias is the one we can control. Okay, so Zener diodes are operated in the reverse bias. And then one more thing, actually, you know what? This is a better drawing. Let's do this. Now, the diode symbol stays exactly the same, except there are whiskers on the cathode. So this is your cathode, this is your anode. Diode voltage is typically measured, not typically, is always measured with a positive at the anode and negative at the cathode. That would be VD. And we would take diode current always going in this direction. This is still true of the Zener diode. But because the Zener diode is used in reverse bias, we associate the voltage and current in reverse. So this cathode terminal would be positive, and the current is flowing in the opposite direction. So VZ and IZ are opposite of the reference for diode voltage and diode current. Okay, so for Zener diodes, we have to alter our thinking a little bit. Okay, cathode will be positive, anode will be negative, and current is flowing from cathode to anode, which again is true because in reverse bias, current is flowing in the opposite direction. Does that make sense to everyone? So our reference is opposite. And it'll make a little bit more sense when we get to the next slide. Any questions so far? So far, so good? Hopefully. Okay. So let's see how it will work as part of a larger circuit. On the left side, we have some sort of DC input going into our circuit, right? So our circuit is here. Okay, this is the Zener diode, and we are providing some input. This is some DC voltage that is being applied, right? Current flows in this direction. We always have a series limiting resistor. That resistor's purpose is to limit the current that's flowing. So not to limit, but the more appropriate technical word would be to control the current that is going into the output. Okay, so this series current resistor, RS, is used to control the total current being supplied. If it was not there, we could possibly exceed the limit of the Zener diode and blow it out. So Zener diode will always be used in conjunction with a series resistor. Series resistor is known as RS. And then you have a load resistor on the far right. So let's say, let's make a simplified version of this diagram. And this is where you're measuring the output voltage. So this is V out, and this is V in. Let's say this Zener diode is rated for 5 volts. Zener diode is rated for 5 volts. Now, if you apply V in, plus here, minus here, if V in is less than 5 volts, is the diode on or off? Diode's off because the threshold has not been crossed over yet. It's simply reverse bias, no current flows through. Okay, so diode is off. No current or very minimal current will flow through. Now, if V in, and not accounting for any other real life conditions, we'll just say it's an ideal diode, an ideal circuit. So greater than or equal to 5 volts, diode turns on in the reverse direction. In the reverse direction. And once it turns on, it's going to start conducting current through it. Okay. So diode is on. IZ is synced through the diode. Current starts flowing through the diode. We don't have any load resistor connected yet. We are simply applying an input voltage, observing the output. And we can do this, again, experiment very easily in the lab too. Have a very small current applied to a Zener diode, apply a appropriate voltage to cross the threshold, and we'd be able to measure the output voltage. Now, this is, of course, just an idealized version, not possible in real life. You know, we'd have to have series resistance and all. But IZ is synced through the diode, okay? if V in increases, what happens? V in increases, you're increasing the power. You're increasing the current that's flowing through the circuit. If V in increases, then I in input current increases, thus IZ increases, but VZ remains constant. Okay, VZ remains constant. And that's it. That's the operating principle of a Zener diode regulator. You can keep on increasing the voltage up to a certain limit, of course, the power handling capabilities of a Zener diode. It'll increase the current that is being supplied to the regulator or the Zener regulator circuit. The Zener current will increase, but it will hold the voltage constant. That is evident. That is evidenced by this diagram right here. Okay. Even the slight curve that is shown here is exaggerated. Once it turns on in real life, we perform these experiments in the lab for other classes. And with the 5.7 volt Zener, there's barely any movement, hardly like millivolts change. So the current increases by a large amount, but the Zener diode voltage remains near constant. And that is what allows us to use the Zener diode as a voltage regulator. Regulation in this particular circuit simply means the input voltage can change, but the output voltage remains constant. So unregulated means V in could be changing, and regulated means it's constant. All right, let's take a pause. You think over that. Let me know if you have any questions. Yes. So the question being asked is, how is the RS functioning in the circuit? I'll address that just in the next few minutes. Does this make sense to everyone, though? We referred to such a device that actually can absorb current in a sense. We call it a current sink. In the lab, we worked with a transistor also that worked as a current sink. So there are devices that can source current, meaning supply the current, or if you have excess current coming from a circuit and you want to create a pathway for the current to flow through ground, that device that allows us to do so is known as a current sink. So it's acting like a sink or a drain to capture all of that current. The Zener diode, when used as a voltage regulator, is known as a current sink. Okay. And then once it turns on, it behaves like a constant voltage source. It's providing a constant voltage at the output with the polarity as shown, plus, minus, plus at the top, minus at the bottom, and acts as a current sink. Okay, let's look at this circuit now. So obviously, if you apply a voltage to this idealized circuit, there is no resistor to limit the current, right? So you would increase the voltage V in, output just keeps on increasing. Beyond a certain limit, the Zener diode could blow out, right? The Zener diode has a maximum power rating capability, PZ. That is the maximum current that the Zener diode can handle, okay? And that can range from milliwatts all the way up to like tens of watts, again, depending on the design and construction. So if you want to control the current and if you want the Zener diode to operate within a certain point, actually, let me back up and explain this circuit without the Zener diode. If there is no Zener diode, and you simply have the series resistor and your load resistor right here. What do the two resistors create? What kind of circuit? They're in series, so what happens to current? It remains the same. What happens to voltage? It gets divided. So it's a voltage divider circuit. It's a voltage divider circuit. Some voltage will be dropped across RS, some voltage is dropped across your load resistor R. Now, depending on the value of RS and R, that voltage could be higher or lower than your VZ. Okay, can be higher or lower than VZ. So when we analyze circuits like these, we are looking for the minimum and maximum values of RS, and we're also looking for the minimum and maximum values of RL, your output load resistor. If either one of those is not within the spec, your Zener diode may not turn on at all. Okay, it may not turn on at all. So if you simply attach a Zener diode here, and not have this RS, if you increase the current, if you increase the voltage V in, the current would increase proportionately. But this output is directly connected to your source. It may inadvertently blow out your Zener diode. Okay, we do not create a voltage divider network. Either your Zener diode would not work, or it would sink so much current that it would blow out. So we add a RS resistor to limit the current. But the value of that RS resistance is typically small. So compared to the load resistor RL, RS would be smaller than R. We want the larger voltage to be dropped across your output load resistor. And then RS typically is a few hundred ohms. And it's 100 to 500 ohms, depending on our application. Okay, so it's not too large. So as an example, let's say we apply, let's say again, this VZ is 5 volts. V in is 10 volts. And you have, let's say for simplicity's sake, 100 ohm RS and R load resistor of, let's say 900. Okay. So what is the voltage across that resistor VR? What is the voltage across that resistor R? 5 volts, but let's say, sorry, let me rephrase the question. Without the Zener diode, what is the voltage across that resistor R? 9 volts, right? 1:9. So VR is 9 volts and VRS would be 1 volt. Okay. So Zener diode would be on, VZ would be 5 volts. Now let's take two cases. If we increase RS, and RS is now, let's say 1 kilo ohm, or 900 ohms for that matter. Okay, 900 ohms. Then what is VR? What is VR? It's two equal resistors, voltage divider network. Voltage gets divided in half. VR is 5 volts. Zener diode will still work. Real life, it may perhaps not work. Idealized circuit, it may work. What if RS or R drops below? If RS is 900, and now your load is not 900 anymore, it's a smaller value. What happens now? Your VR is now less than 5 volts. Therefore, diode will not turn on. No regulation will occur. Okay, because this R is small, so instead of the current going, maximum current going through Zener diode, most of the current would go through here, causing a smaller voltage drop. If it's a smaller voltage drop, your Zener diode is not going to turn on. So the Zener diode regulator circuit requires a design where there is a minimum value for the load resistor. Does that make sense? Again, RS and R are creating a voltage divider network. And because they're creating a voltage divider network, the Zener diode depends on voltage at the output to turn on. If the load resistor is small compared to the series resistance, a smaller voltage will drop across the Zener diode. Zener diode will not turn on, and your circuit would not work. There is the other possibility where the RS value is too small, so the current coming from the supply is too large. If the current from the supply is too large, Zener diode, the Zener current will increase. And because the Zener current increases, there's an upper limit governed by the power rating of the Zener diode. Okay. And we'll talk about that in next class. So PZ power rating. Max or IZ max. All right. We'll end class here today and we'll pick up here again on Wednesday. I'll assign a reading. I think I may have already assigned it. I can't quite recall. But on Zener diode, there's a section of the textbook, and there'll also be a homework coming up due probably Wednesday or Thursday. Okay.